Okay, so the final part of impulse and momentum, okay, is going to be a collision between two spheres. Okay, now these two spheres are going to be coming at each other at different angles. Okay, so not coming head on. Okay, so there's a few little steps that we can take to ensure that we're like tackling this the best we can. Okay, so in this scenario, we can define our axes wherever we want to define them as. Okay, so in these scenarios, we're going to make sure that we define the axes as following. Okay, to make sure that the centers line up, and that's what I'm going to call my x-axis, which means everything I've got, I think, in the perpendicular direction is y. Okay, so just be careful of like at different angles that we can be dealing with at this point. Okay, make sure we make our diagrams big enough to label all those kind of angles. Okay, so we're going to firstly show, it says here, the points. Okay, show the line to the center. Okay, use this to define your axes, as I just said. And then the other thing is going to express their initial and their final velocities as vectors before we go any further. Okay, so that's going to help me. Okay, so make sure that we're writing angles on all that kind of stuff. Okay, now if they're smooth, which they will be, okay, then the impulse during the collision, okay, will only be along the centers. Okay, which means straight away everything in the y direction, okay, as in your velocities in the y direction, are gonna stay the same. Okay, so very similar to the one we just did with the wall, hitting the wall. Okay, we can make sure that that y direction is going to stay the same, so it makes it easier for ourselves. Okay, which means that only things in the horizontal direction, okay, so in the parallel direction, are the ones that can be affected by your impulse. And they're exactly the same kind of idea for your coefficient of restitution. Okay, E is only going to work then in the x direction, not in the y direction. Okay, and then we can also apply conservation momentum along the lines of center. So we don't have to look at the whole vector. We can just look at the things in the x direction again. Okay, so us defining our axes allow us to simplify the question for ourselves, okay, because it makes things in the perpendicular, sorry, if I say the word correctly, perpendicular direction stay the same, okay? So let's jump into this question, okay, and we'll think about how we're going to tackle it. So the diagram shows the velocities of two small spheres of the same radius just before they collide. If the coefficient of restitution between the two is a half, find the velocity of two spheres after the impact. Okay, so define everything here for me. So the first one, I've got it 12 and it's going at 30 degrees. This one's at 10 meters per second, moving at 6 degrees. Okay, and then afterwards they've got velocities of alpha. V1 is alpha beta, and V2 is gamma and delta. Okay, so we'll just use those two values they've given me. Okay, but the first thing I need to do, so in this case, because I can define their centers as here, so I can just use a normal set of axes. So I've done the first one. I've defined my axes. My next thing I'm going to do is I want to express them as vectors. So these second ones already are. V1 is alpha beta. Okay, and V2 is gamma and delta, if I can draw my delta correctly. There we go. Okay, now my U1 and my U2 is going to be my other bit, so I'm going to do some bit more work on. Okay, so U1, let's apply some trig like we normally do. So I've got 12 cos 30, and I've got 12 sine 30. And then very simple for this one, for U2, I'm going to have 10 cos 60, and I'm going to have 10 sine 60. Okay, now in this scenario, I'm going to just type these in my calculator and see what they come out as, because I know they're going to give me quite nice ones. The first one is 6 root 3 and 6. And the next one is 5 and 5 root 3. Okay, now, from that, I can instantly change these V1s and V2s. Okay, because I know that the only things that are going to be changing are in the x direction. So everything in the y direction must be staying the same. So that means beta must stay as 6. So alpha, it's going to be alpha and then 6. And then the y component on this one's going to stay the same. So I stay with gamma, and then I'm going to have 5 root 3. Okay. So that's my starting point. Okay, now I'm going to use my two things. I'm going to use my coefficient restitution, and I'm going to apply conservation of momentum. So let's start with coefficient restitution. So I've got E is a half. Now it should be my speed of approach over speed of separation over my speed of approach. Okay, so my speed of separation, okay, in the diagram that they've given me here, okay, they're both moving in the same direction. Okay, so I'm going to make sure that I subtract them. So I'm going to have gamma minus alpha. That's how far this one's moving away compared to this one. Okay, now my speed of approach, okay, they're moving in the same direction again, so I take them away. Okay, so I'm going to have 6 root 3, okay, minus 5. Okay, that's how far they're approaching. Okay, and from this, I'm just going to rearrange and solve a little bit. Okay, so I'm going to have gamma minus alpha is 3 root 3 minus 2.5. Okay, now I can't really do anything with that right now because I've got 2 unknowns. So let's just call that equation 1. Okay, and now let's use conservation of momentum. And we're going to make sure we do it along the center. Now, when I say this, I just mean the x direction, x components. Okay, so I don't care about the other components. So initial momentum, I'm going to have the first mass was 10. So it's 10 times 6 root 3. And I'm going to have plus 8, because that's the mass of the other one, times 5. And that's going to equal 10 alpha, because I don't know what alpha is, plus 8 gamma. Okay, and I'm going to simplify this a little bit. Gives me 60 root 3 plus 40. Okay, now yes, I know I could simplify this even more. Okay, and like divide everything by 2. But there's no need for me to do that. Okay, I can just solve these simultaneously. Okay, so I'm going to solve 1 and 2 simultaneously. Okay, is going to give me alpha is 6.797 and gamma is going to be 9.494. Okay, so I can now do my V1 equals and my V2 equals. Okay, so V1, alpha is 6.797, and we said my y component is going to stay the same. And then the other one is going to be 9.494, and it's going to be 5 root 3. And there are my final 2 answers there. Okay, so key bits, if you've got 2 objects and they're coming at each other at angles, okay, make sure your velocities are written as vectors, then use your coefficient restitution and use conservation of momentum along the center, so only the x components. Okay, define your axes however you want. Okay, but wherever you do define them, make sure you then start to work with angles as well. Okay, so that's it for impulse and momentum. Okay, there are past period questions. Okay, so have a go at some of these. Okay, this is kind of like hitting a wall and stuff like that. So look at that one. And then we've got this one, which has got 2 smooth particles that hit. Okay, so we can define how we want. And we've got our things there. And then we've got some EdXL past papers. So again, we can search up the year of EdXL and find them if you need them. Okay. But apart from that, okay, I'll see you in the next topic.